Hello everyone, this is Miss Haneen Khair from Al Shumukh International School. In this video, I will explain how to write a cell diagram and how to use the E0 of the cell to predict the feasibility of reactions. So the cell diagram is a representation of the overall reaction that's taking place in an electrochemical cell. We can refer to it as cell diagram, cell notation, shorthand notation, it's the same thing. The anode is always written to the left, the cathode is always written to the right of the cell diagram. So you start with the anode and you end up with the cathode. The two vertical lines in the middle represent the salt bridge. The solid line represents the phase change. If you have solid and then aqueous within the same compartment, you separate them by a solid line. So as we said before, the double vertical lines represent a salt bridge. The single solid lines represent a phase change between the solid metal and the aqueous metal ions. As you can see, in the electrochemical cell made from zinc and copper compartments, zinc has the more negative E0, so it's placed at the anode to the left of the cell diagram. So I'm starting with zinc solid line, then Zn2 plus. This is the compartment of the anode. It's made up from zinc metal and Zn2 plus ions. The two dashed lines, the two solid lines, are representing the salt bridge. Then the cathode is made up from Cu2 plus ions. There is a phase change from aqueous to solid, so there is a solid line separating Cu2 plus and Cu. When the electrode is a piece of platinum foil, sometimes you don't have a metal, like in H plus H2, in Fe3 plus Fe2 plus cells, you don't have a metal to conduct the electricity. We use a platinum foil in order to compose an electrode. The convention is to show the least oxidized species in the half cell next to the electrode. So for example, you have Fe3 plus Fe2 plus. You can see here we are using comma because there is no physical change. There is no state change between Fe3 plus and Fe2 plus. The solid line is used between Fe2 plus and the platinum. Notice that because there isn't any change boundary between Fe2 plus and Fe3 plus, a comma is used, not a solid line. The standard hydrogen electrode is represented as follows: 2H plus H2 PT. So you can see that we have two solid lines because between H plus and H2 there is a change of state. Between H2 and platinum there is a change of state. When measuring the standard electrode potential, the standard hydrogen electrode is always placed at the left hand side. So by convention, if you want to measure the standard electrode potential of a certain metal, you have to place the standard hydrogen electrode, the She, on the left hand side. So in this case, you can see that Cu2 plus Cu has a positive value, E0 value. Therefore, it is acting as a cathode and the electrons are flowing from the anode to the cathode. So PT solid, H2 gas, 2H plus aqueous, two solid lines representing the salt bridge, and then Cu2 plus Cu. When we are connecting Zn2 plus Zn, you can see that the E0 measured is negative 0.76. So compared to H plus, Zn2 plus is less reactive, or compared to H2, Zn is more reactive, and that's why you got a negative value. So to get a positive value, the She has to be placed on the right side and Zn2 plus Zn compartment on the left side. So the sign of the E0 of the cell indicates the polarity of the right hand side with respect to the standard hydrogen electrode, whether it's more reactive or less reactive. If the E0 is more positive, then the metal is less reactive than hydrogen. If the E0 is negative, then the metal is more reactive than hydrogen. A large negative value of E0 indicates a highly reactive metal that is easily oxidized. A large positive value of E0 indicates a highly reactive metal ion that is easily reduced. We already covered this material before. So a high negative value of E0 means that the metal can undergo oxidation really easily and the metal ion cannot be reduced that easily. If the E0 is positive, then this means that the metal ion can be reduced really easily and the metal cannot be oxidized that easily. The standard electrode potentials can be used to measure how easily a species loses electrons. This indicates how far to the left the equilibrium shifts relative to the equilibrium in the standard hydrogen electrode. So for example, if E0 is negative, then this means, let's say considering Zn2 plus 2 electrons forming Zn, the E0 is negative 0.76. This means that the equilibrium shifts more to the left than to the right because Zn is more easily oxidized. However, in case of copper, Cu2 plus 2 electrons forming Cu has a positive E0, so therefore the equilibrium shifts to the right toward the formation of Cu, the reduction of Cu2 plus, and the formation of Cu. So the position of the equilibrium of the Zn2 plus Zn reaction lies furthest to the left than that of Cu2 plus Cu, so therefore zinc is more reactive than copper. If the zinc and copper half cells are connected to make an electrochemical cell, electrons will flow from the zinc to the copper electrode. Because zinc is more reactive, it can be easily oxidized, more easily than copper can be oxidized. So therefore, zinc is losing 2 electrons. The electrons are moving through the wires to the Cu. If you connect a high resistance voltmeter, then the EMF of the cell can be measured. The E of the cell can be measured, which is plus 1.1 volts. Of course, the salt bridge, as we discussed before, is used to maintain the electron neutrality of the cell and to complete the circuit. Predicting thermodynamic feasibility. How to use E0 to predict the thermodynamic feasibility, whether the reaction is going to take place or not. An example is, will chlorine oxidize manganese ions to manganate ions? The E0 values are given. As you can see, the E0 value for the couple MnO4 minus Mn2 plus is more positive than the E0 value of the couple Cl2 Cl minus. This means that the equilibrium in the first half reaction tends to lie more to the right. So MnO4 minus is going to be reduced to Mn2 plus, and Mn2 plus cannot be easily oxidized. However, in the second half reaction, the E0 is less positive than the first half reaction, so the equilibrium will tend to lie to the left. So therefore, this reaction is thermodynamically isn't feasible. In order to explain it more, check this out. So these are basically what you're starting with, the ones that are in green circles. You're starting with Mn2 plus and Cl2. The value of the E0 of the couple MnO4 minus Mn2 plus is more positive. So the equilibrium in the first half reaction will shift to the right rather than to the left. So Mn2 plus is not easily oxidized. However, in the second reaction, the E0 is more negative compared to the E0 of the MnO4 minus Mn2 plus. Therefore, the equilibrium in the second half reaction will lie furthest to the left. So therefore, Cl2 cannot oxidize Mn2 plus. Another example in predicting thermodynamic feasibility. Will magnesium react with dilute sulfuric acid? The E0 values are given below. The Mg2 plus 2 electrons giving Mg half cell has an E0 of minus 2.37, and the H plus H2 redox couple have E0 of 0 because this is the standard electrode. So therefore, the E0 of the Mg2 plus Mg is more negative. The equilibrium lies furthest to the left. So therefore, Mg can be easily oxidized. H plus H2 E0 is more positive. The equilibrium lies furthest to the right. Therefore, H plus can oxidize Mg, and the reaction is feasible. In order to understand it better, these are the Mg and a 2H plus present in green circles are the reactants you're starting with. E0 value is more negative. The equilibrium will shift more to the left. E0 value of H plus H2 is more positive, so the equilibrium will shift to the right, and the reaction is going to take place where the electrons will flow from magnesium to H plus. The last example of predicting thermodynamic feasibility is copper. Will copper react with dilute sulfuric acid? So as you can see, copper Cu2 plus Cu has a more positive E0 value. Therefore, the equilibrium will shift more to the right. So Cu can't be easily oxidized compared to H+, where H+ and H2 couple has a more negative E0 value compared to that of Cu2 plus Cu. So the equilibrium in the first half reaction will shift furthest to the right. The equilibrium in the second half reaction will shift furthest to the left. So therefore, the reaction is thermodynamically not feasible. Again, re-explaining it, you are starting with Cu solid and H plus. You have E0 value of Cu2 plus Cu is more positive, so the equilibrium tend to move to the right. The E0 value of H plus H2 is more negative or less positive compared to that of Cu2 plus Cu, so the equilibrium will move to the left. So the reaction is thermodynamically not feasible. Now, what are the limitations of predicting thermodynamic feasibility? Some reactions are thermodynamically feasible, however, they do not take place because they have a very high activation energy, so therefore it's kinetically not feasible. Another reason is that many reactions may be carried out at not standard conditions. So we cannot guarantee that the conditions are really standard. So the temperature is 298, the pressure is 1 atmosphere, and the concentration of the solutions is 1.1 mole per decimeter cube. We already said before that the sign of the standard electrode potential doesn't change when reversing the half equations. However, just to predict the feasibility of the reaction, an alternative method is to reverse the sign of the standard electrode potential to the proposed reaction. And just to meet the proposed reactions, invert the sign. It's scientifically incorrect, but it's always working. Just invert the sign, find the E0 of the cell by combining the two E0s, and then you can tell if the E0 of the cell is positive, the reaction is thermodynamically feasible. If the E0 of the cell is negative, then the reaction is thermodynamically not feasible. Despite the imperfect science, this method does produce a correct answer regarding the feasibility of the reaction. Because we said just by predicting to which direction the equilibrium will shift, there are some limitations. So this one will give us more idea about the feasibility of the reaction. So we have a proposed reaction between zinc and copper. So it's going to be Cu2 plus Zn forming Zn2 plus and Cu. The two standard electrode potentials are given below. Zn2 plus 2 electrons forming Zn. The E0 is negative 0.76. Cu2 plus 2 electrons is forming Cu. The E0 is 0.34. Because the reaction in the proposed reaction Zn is undergoing oxidation, you are going to flip the sign of the E0 of Zn. So it's going to become plus 0.76. And when we add them, we're going to get plus 1.1 volts. So the reaction is thermodynamically feasible. So to predict the feasibility, write the two half equations as they occur. Zn is plus 0.76, Cu is plus 0.34, and the E0 of the cell is plus 1.1, so it's positive, then the reaction is feasible. To practice feasibility, we are going to do these reactions. The first one, Fe3 plus Cl minus, giving Fe2 plus half Cl2. Is this reaction feasible? In the reaction, Fe3 plus is converted to Fe2 plus, so the sign of the E0 is going to remain the same. Cl minus is being converted to Cl2, so E0 is going to be flipped. So it's going to be 0.76, negative 1.33. The E0 of this cell is negative 0.57. So therefore, this reaction is thermodynamically not feasible. The second reaction, again, Fe3 plus is reacting to form Fe2 plus. So the E0 is going to remain as plus 0.76. However, I minus is being oxidized to form iodine. So the second half reaction is the E0 of which is going to be flipped. So it's going to be 0.76 minus 0.53. 0.23, positive 0.23. It's always a good idea to include the sign, whether positive or negative. So the second reaction is thermodynamically feasible. Third reaction, Br2 plus 2Cl minus, forming 2Br minus plus Cl2. So the Br2 is written as, the Br2 is being reduced, the Cl minus is being oxidized. So the E0 of the Br2, Br minus couple is going to be the same. We're not going to reverse the sign. Whereas the Cl minus is undergoing oxidation in the proposed reaction, so the E0 is going to become negative 1.33. As you can see, negative 1.33 is more negative, so the final E0 is going to be negative. E0 of the cell will have a negative value, so the reaction is thermodynamically not feasible. The last reaction is Fe3 plus reacting with electrons, gaining electrons to form Fe2 plus, the E0 of which is plus 0.76. We're gonna keep this as it is because it matches the Fe3 plus in the proposed reactions. However, Br minus is being oxidized to Br2, so therefore this one is going to be negative. 0.76 minus 0.1.7, the value is going to be negative, so it's going to be thermodynamically not feasible. So it's going to be not feasible, feasible, not feasible, feasible. I hope you find this helpful. This is the end of our third video. Thank you for watching.